exciting that this topic is here now, finally, at NeurIPS. Okay, great. Okay, so we know that simple models often perform well. And I'm talking really simple models, like ones that can fit on an index card. And for tabular data sets, they often perform on par with deep neural networks. So let's give you some examples from a couple of high-stakes domains. And we're going to ask, empirically, how many leaves in a decision tree do you need to get to within 1% of black box accuracy? And say these black boxes can be deep neural networks with tons of weights. So what's the answer? Maybe you're thinking 30, 40, 20 perhaps. Well, it's a bit smaller than that. So for 4 criminal justice data sets, you don't need more than 10 leaves. And for credit default risk data sets, you also don't need more than 10 leaves. Right? You think complex models would do better, but they don't. And you could pretty much guess from what I'm showing you what would happen if we tried more recidivism data sets, right? Right? You get the same thing, right? Like if I didn't tell you the answer for one of these, you'd probably be able to kind of guess what it was. Right? These data sets are just not benefiting from extra complexity. So these are ordinary data sets, but what do they have in common? Now, these data sets all have noise between the inputs and the outputs. Okay? The outcomes are not deterministic. Right? You don't know whether someone's going to be arrested after they're released, right? There's a lot of factors that determine that, like whether someone's going to get a job or whether somebody's going to go to college or whether they're going to have children, right? Whatever. These are sources of randomness that are not available in advance, okay? The outcomes are just plain uncertain. And what I want to explain to you is this noise is an inherent driver of simplicity. Yeah, my collaborators and I have been trying to understand this phenomenon for a while, and I'm going to talk to you about the latest paper that we have on this project. It is this one right over here. And this is joint work with my amazing collaborators, Zach Boner, Harry Chen, Leslie Semenova, and Ron Parr. And what we found is that noise is an implicit regularizer, okay? So what's noise? All right, noise means that the class label is not deterministic. Like if you have 9 medical patients with identical medical records, it's possible that 5 of them will have a heart attack next year and 4 of them might not. Now in image recognition, it's not the same. If you've got 10 identical images, either they all have a chair in them or they don't. Right? So there's no noise here. All right, so what the result is saying is that if you have noise, it corresponds to increased regularization, and you know that by definition, more regularization leads to simpler models. Now, there's past work on this kind of general area dating back to Bishop in 1995 for ridge regression, and there's a whole bunch of recent work on stochastic optimization, providing regularization, which has absolutely nothing to do with noise in the data, so that's different because our results are algorithm independent. And what we wanted was something that's really clean here. We wanted like a really clean result for classification. Now, my collaborators and I have been working on the existence of simpler models for many years, but we wanted to get like a more concrete handle on this relationship. So specifically, we wanted to know how much noise in data generation leads to how much regularization. So let's go ahead and ask this question. So given that our data has noise level rho, say uniform random label flipping noise, okay? How much simpler do machine learning models get as compared to the non-noisy case as if we had cleaned up our data, right, and adjusted the regularization to get the same objective? And more importantly, why should we care about this? Well, this is at the core of what we do, right? If we know the data has a noisy generation process, for whatever reason, if we can determine how simple a model we might need, we can say, look, we don't want to make decisions about people's freedom or about people's finances based on problematic complex models, right? We can govern in advance that for high-stakes decisions, complex models should need to be heavily justified if there's an inherent level of noise in the data, right? And the idea is to know something about simplicity in the models before even seeing the data, okay? And that's what gives you the ability to make policy suggestions. You got to know something about the problem before you see the data. Okay, so let's go to something more concrete. So I'm going to talk about regularized misclassification error, so just 0-1 classification error, okay, and random label noise. So here I have 0-1 loss, I have my hypothesis space, it can be any hypothesis space, linear models, decision trees, additive models, whatever you like. I have my regularizer with regularization parameter lambda. It can be whatever regularizer you like. It can be the number of leaves in a tree, it can be the number of terms in your model, whatever. And then I have my noisy distribution and my clean distribution. And just when I say clean data, I don't really mean clean. I don't really mean clean. I just mean data without the flipping noise. So what's the flipping noise, okay? So the flipping noise goes like this. So given rho, which is a number less than 0.5, so between 0 and 0.5, each clean label is flipped with probability rho, meaning that the new label, the noisy label, and the clean label are different with probability rho, okay? So clean data is just data without this extra flipping noise, okay? All right. So, you know, you can think of data having some inherent level of label flipping noise. All right, and the theorem goes like this, where optimizing this is a 0-1 loss with regularization penalty lambda and outcome noise level rho is equivalent to optimizing on the clean data distribution, so removing the noise, if you could do that, with a stronger regularization parameter, lambda over 1 minus 2 rho. So this is bigger than that, okay? And so again, it says that whatever you're doing on the noisy data is equivalent to a more regularized version on the clean data. And you can't actually remove the noise in practice, right? So you just get simpler models. So again, it says optimizing over the noisy data distribution is equivalent to optimizing over the clean data distribution with stronger regularization penalty lambda over 1 minus 2 rho, which induces simplicity, okay? And this theorem applies for any class of functions and any regularization for 0-1 loss, okay? And including sparse decision trees, sparse generalized additive models, sparse rule lists. These are my favorite three of my favorite classes of models here. Okay. And it can be regularization on the number of leaves, on the number of terms, or on the list length, whatever it is. So basically, for any hypothesis space with regularization, with any regularization function, this theorem holds. All right, so here's another way to see what's going on. Okay? So same assumptions, same setup. Here are the optimal models over the clean and noisy data distributions. And the second theorem says that either the noisy and clean models are the same complexity, or the noisy model is strictly simpler. Okay, the noisy model is never more complex. Okay, so what happened here is that the increase in the regularization parameter from theorem 1 made the noisy model simpler. Okay, so let's show an experiment to see these theorems in action. So I'm going to optimize 0-1 loss with sparsity regularization in two ways. The first way is to add some noise, rho. And I'm going to repeat this so one single noise draw doesn't have too much of an effect. And then I'm going to use my regularization penalty lambda, and I'm going to compute an optimal model. And then the other way I'm going to do this is I'm not going to add noise. I'm going to use the data set as it is and use a regularization penalty lambda over 1 minus 2 rho. So it's that larger regularization penalty from the theorem. I'm going to see if these two things give you the same result. All right? And to do this optimization, I'm going to use the GHOST algorithm. So GHOST is an algorithm that computes optimal sparse decision trees, like actually optimal sparse decision trees, balancing 0-1 loss with the number of leaves in the tree. So it's actually doing precisely this optimization. And so let's see the result. Okay, so what I'm showing you is complexity measured by the number of leaves in the tree versus the noise level rho for 4 recidivism data sets, and they're right here, okay? 4 data sets right there. And then the solid line is the optimal model over the noisy data, and then the dashed line is the optimal model over the clean data with the extra regularization. And of course, they're not quite the same because noise is random, and so you do get a little bit of randomness from that noise. All right, and so the results show just what the theorem says, which is that adding noise is equivalent to adding no noise and upping the regularization. And the models get, the important thing here is the models get simpler with more noise, right? As you go over to add more noise, the models get simpler. So for example, with the Broward County data over here, this orange one, you know, when 10% of the labels are flipped, just over here, the optimal model goes from 9 leaves at the beginning with no noise to 4 leaves when you have noise, okay? All right, and we're seeing the same thing for a bunch of loan decision data sets as well. All right, so on the next slide, I'm going to present an analogous result for the exponential loss with linear models and noise in X. So the previous result was for 0, 1 loss for any type of model and for noise in Y. Okay. So I'm going to let epsilon be this kind of jitter. So we're going to jitter X with a jitter of size rho, and we're going to add this to all the data. And it turns out, and I'll show you the theorem in the next slide, that this adds implicit L2 regularization with regularization parameter 1/2 rho squared. All right, so let me show you that. So here's the setup. We have the exponential loss. We have our space of linear models. We have our clean data and our noisy data. The exponential loss, of course, is the same loss used in boosting. And the theorem goes like this. Okay, this is theorem 9 in the paper. It says the minimum of the exponential loss equals the minimum of this guy over the clean data plus, and then here's a regularization term. This term was not here before. It's adding regularization, creating simpler models. And then here's an experiment to show this, right? Same thing as before. As noise goes up, right? As the noise goes up, complexity, which is this, goes down. And this is on 5 different data sets. All right, so the optimal models get simpler with noise. However, it's not just the optimal models that get simpler with noise. The whole class of good models gets simpler with noise. So I'm going to define the Rashomon set as the collection of almost optimal models. Okay? So this is my objective. These are the models in the hypothesis space that are almost optimal. They're near optimal. All of them have objective within theta of optimal. And as it turns out, the whole Rashomon set contains simpler models when you add noise. So here's an experiment to show this. These results are aggregated over 23 different data sets, showing the sizes of all the near optimal decision trees on these data sets. And what I'm showing you is that the near optimal models become simpler as you add noise. So here there's no noise, and the models start out at kind of larger sizes. And then as you add noise and you look at the Rashomon set each time, those models tend to get smaller as we add more noise. Now, a nice way to see what happens here is to look at the models in the clean and noisy Rashomon sets. So there are 3 types of models. Models just in the clean Rashomon set, okay? And then models in both of the sets, and then models that are only in the noisy data's Rashomon set. And as it turns out that under mild assumptions, models only in the clean Rashomon set are strictly more complex than the optimal model for the noisy data. And models that are in the noisy Rashomon, only in the noisy Rashomon set, are strictly simpler than the optimal model for the clean data. Okay, and these results are proven in some theorems in the paper. But the important bit here is that the noisy Rashomon set contains either the same complexity or simpler models than the best of the clean data models. Okay, so the class of good models gets simpler. And another thing that happens is that the best features tend to degrade faster with noise. Now, I often use the AUC of each individual feature to measure how good it is. Right? Features with higher AUC, they look more like the label Y. Now, as it turns out, features with the highest AUC degrade faster as we add noise to the data. And we have a couple of theorems about this in the paper showing exactly how that works. Here's one of them, which relates the AUC of a noisy feature to the corresponding AUC of the clean version of that feature. But this one is easier to see through experiments, so I'll show you an experimental result. And this is a histogram of AUCs of features aggregated across all of the criminal justice and loan decision data sets I was showing you earlier. So this is clean, this is noisy, so clean on the left, noisy on the right. And you can see here that the best features AUC degrades as we add noise. Right? There aren't these few good features anymore. And what this means is that when you're in the noisy setting, there ends up being more possibilities for features to use in your models. Because you don't just have a couple of good features anymore. Now you got a whole bunch of features that seem about equally good. And so this expands the pool of good models so you can get bigger Rashomon sets when you have more noise. All right, so I've shown that noise is an implicit regularizer. I've shown it for 0-1 loss, for any model class, for any regularization function. I've also shown it for the case of exponential loss with linear models and L2 regularization. I've also shown that the whole Rashomon set, so all of the near-optimal models, become simpler. The set of functions becomes simpler under noise. Like all of those functions in there become simpler. I've also shown that the best features degrade more quickly under noise, which leads to larger Rashomon sets, so more opportunities for good models, or equally good models. Now, one glaring thing I have not discussed is how to create these simpler models. And if anyone should know about this, it's me, because my lab works on this. All right. So for sparse decision trees, we've got a ton of algorithms, and I've listed only some of them here. We have the ghost algorithm that I told you about earlier, which produces truly optimal sparse decision trees. The word generalized means it optimizes different objective functions. We have the tree farms algorithm that gives you entire Rashomon sets of decision trees so you can have users look through them and find the trees they want. We also have optimal sparse regression trees for regression. We have optimal sparse survival trees for survival analysis. And now we have also sparse density trees and lists, which are a high-dimensional alternative to histograms. If you like sparse generalized models, I love sparse generalized additive models. Rich Caruana does too. He's going to give the next talk after me and talk all about them. And his work inspires me to work on this too. I love this type of model. They're very powerful, very beautiful, and very simple. So here I've put a whole GAM on a slide right here. So you just take nonlinear functions of the variables and add them up. That's the whole model. And we have the fast sparse algorithm for producing sparse generalized additive models. We also have the new MGAM algorithm that handles missing data in a beautiful, elegant way that doesn't involve imputation. We have the Oak Ridge algorithm that does sparse ridge regression, and it's even useful for learning dynamical systems, for learning the terms in dynamical systems. We have the new fast survival algorithm that does Cox proportional hazards models, gives you very sparse models, sparse GAMs for that. And we have the GAM Rashomon set algorithm, which allows you to find Rashomon sets for GAMs. And these two are just this conference here. If you like risk scores are sparse GAMs with integer coefficients. So you would add up the points, right here are the integers, integer coefficients, you add them up and you get a risk from a table. And you create these models from data is very difficult because you get all kinds of integrality, you get sparsity constraints and integrality constraints. And we have algorithms for this too. We have the faster risk algorithm, and then we now have the group faster risk algorithm. Now, if you don't care about global sparsity of your models, but you want your explanations to be sparse, like your counterfactual explanations to be sparse, you might want to try one of these two algorithms. So these algorithms optimize what we call sparse explanation value, which is a natural kind of counterfactual explanation, where if you take one of the feature values and move it to kind of a standard usual value, it flips the sign. All right, and if you're interested in interpretable neural networks, you could try the new prototype transformer models that we have, also again, a NeurIPS 2024 paper, so brand new. So this does computer vision with interpretable prototype models that use transformers. And then, if you're not sure exactly what your data has in it, one thing you could do is take the data, project it down to 2 dimensions, and figure out what's in it. And that's what these algorithms for dimension reduction do. And so I've put here the param repulsor result on MNIST, which beautifully separates the MNIST into 10 classes without a model. It's just looking at the raw data and projecting it down, and you can see already the 10 classes separated. All right, cool. So just to summarize, if the data come from a noisy process, meaning non-deterministic outcomes, models are more heavily regularized and are thus simpler. The set of best features expands and creates larger Rashomon sets. And we can find simpler models. Now, we have both theory and algorithms that support the development and use of simpler models in noisy high-stakes decision domains. We should care about this. This matters because without even seeing the data and just knowing how noisy the generation process is, we might be able to rule out the use of overly complex models. Thank you.
So great talk, really refreshing to see this kind of opinion. I thought I was the only one that thought like this. Quick question though, if your data implicitly has noisy labels, kind of at the 90% level, and you're kind of training with additional noise, do you find that then if you can somehow reveal the truth of the labels, do you find your model implicitly does better than the natural labeling accuracy of your data after you've used this approach?
Okay, so I kind of realized that I wasn't being as clear as I'd hoped. So what you get is the noisy data. You never get the clean data. You can't remove the noise from the data. It's impossible. All you know is that the generation process for the data itself has some level of noise in it. Like for example, with criminal recidivism data, you just know that these people are going to go out into the real world and some of them are going to flip randomly to whatever you think. So that's the level, that's the noise that I'm talking about, the noise that comes with the data that you can never remove. So we never add noise to data. Never. We just get the noisy data.
So, okay, thank you.
Sure. Yeah, so I'm just saying, if the data has that property if the data has that property already, that it's noisy, then it's equivalent to as if I had removed the noise from the data and added more regularization. So it's as if that happened, but that can never happen. So it's saying that even if you clean that data up, you're implicitly getting simpler models than if you had, just optimized on the clean data. So there's no way to get around it. You just can't. You're stuck. Yeah, that's the idea. Thank you for asking that.
My question's about noise. It's it seems from the analysis that you assume the same noise everywhere. Is there any hope of getting similar results when noise is not added the same way everywhere?
Yeah, okay. So that's a good question too. These results were easier to obtain because we use the uniform noise. Another type of noise we use is margin noise, where you basically have two Gaussians and you shove them together so that you get a lot of noise on the margins, but not necessarily noise kind of out in the distance. And so what I'm hoping to do is kind of approximate the real world by a combination of uniform label flipping noise and margin noise. I'm not sure if that's completely realistic, but I feel like it's realistic enough that it would represent kind of the levels of simplicity that we actually kind of are seeing in the criminal justice and whatever problems. I think that there is a kind of level of uniform label flipping noise in a lot of these problems anyway. Like with criminal recidivism, even if there's extra margin noise, there's at least uniform label flipping noise just from the fact that humans are entering numbers by hand, or that random things happen to people like when they get out of prison and we don't know, right? So there's just some level of noise implicitly in the real world, and that is the noise that you have at least that noise, right? So you get at least that simplicity, and if you have more noise, you get more simplicity, right? So that's where I'm hoping to go with this. But as you can see, I've been working on this for a long time, and I've been working on interpretability since I don't even know 2007. I don't know, but this was at the time where when I started doing this, there was no possibility that NeurIPS would have an interpretability workshop. That would never exist. No papers on interpretability were getting into NeurIPS because nobody cared about it. And so, you know, I'm coming from that perspective where you've got people who are saying, but I don't want to sacrifice any accuracy, no accuracy. And it's like, well, but I want to prove to you that you're not going to. I want to prove that. And so that's where this whole thing came from.
I was wondering when the results came out that when you inject noise in the data sets, that simpler models actually perform better. Well, I was wondering whether this occurs because the number of relevant data actually drops, and when there's fewer data, well, simpler model work better.
I'm not sure that the number of relevant data drops. It's just that each data point is sort of kind of giving you less information about the label than it was before, if that makes sense. You know, like if I label an image that has a chair in it, that it has a chair in it, like I can believe that. Like that's 100%, that's a chair. Whereas with a medical patient, you know, I go, well, I don't think he's going to have a heart attack next year, but I'm not sure, right?
Yeah.
And so the data, all of the data become a little bit less valuable in that sense for telling you about the label, right? That's what this AUC result was. That's what all these AUC results were. They were about sort of showing that each variable is kind of, you know, the really valuable variables become less valuable very quickly.
So in a parallel line of work, actually there is a scenario where we add noise to data. In deep learning, it's called data augmentation, and it has shown to like improve the robustness of models in general. And there are also some theoretical, there's also some theoretical work on how it regularizes the models. So I just thought, what's your opinion on that?
Again, so noise does add regularization. And it sounds like they're using that noise to just add regularization because they were overfitting before. So they're kind of leveraging this noise. I don't know how adding that noise compares to just adding more regularization on the weights. So they might be doing kind of the same thing. I guess our results would kind of indicate that they might be doing the same thing. But
I think so.
I think with neural networks, people have tried all kinds of weird stuff to try to get it to regularize. But so, like I mentioned, there was a result in 1995 from Bishop that adding more noise induces L2 regularization for ridge regression. So it's already known for ridge regression, but you know we're interested here in classification and exponential loss, which is also for classification. So 0-1 loss, exponential loss.
Yeah, I also wanted to make this comment about ridge regression, that this is a really nice didactic example because you see it in the analytical solution that you just add noise to the data covariance. But I also wanted to follow up on the question of what types of noise do you consider? Because I think it could also make sense to consider correlated input noise, which is realistic in some applications. And my question is, how does this affect simplicity? For example, I can imagine that a decision tree might have a hard time in the presence of correlated noise because it needs to zigzag around the input space to find the optimal decision.
Okay, so I'm not sure what this type of noise is because the earlier result that I showed was for kind of noise between the X and the Y. So you must be talking about noise between the X's somehow.
Yes.
Okay.
Yes.
Yeah, I'm not sure. I mean, like I said, there's a lot of different kinds of noise, and we've only studied a few. But I think that's maybe something we could think about in the future.
Okay. Thanks.
Thank you.